In this video, I'm going to finish up the so-called analytic method of looking at solutions to the Schrodinger equation in one dimension with the potential modeled as a harmonic oscillator. And in the previous video, we saw that we could get our coefficients of a n plus 2 in terms of a sub n. And so we can separate this because this goes up by 2 every time into two different summations. So we have our f of xi is equal to a summation, and I'm going to change the summation index here, so I'm actually going to change that on here, so a sub m. And the reason I'm doing that is because we're using n as the energy levels, so we're using this as energy levels, or energy at these different n levels here, and so I'm just changing the summation index on these, and that will go from m equals 0 to 4 and so on, and that will go up to n because that is where we are terminating it, and that is a sub m times xi to the mth power plus the summation where m equals 1, 3, 5, and so on, going up to n a sub m xi to the mth power. And so we can separate it based on even and odd like this. And we also want, like I said, we want this to terminate. So we had our relation where it was a sub m plus 2 was equal to 2m plus 1 minus our epsilon n over 2, or m plus 2 times m plus 1, and that was times our a sub m. And we said that this right here has to terminate when the numerator is 0, and we said that that will be the case when this is equal to 2n plus 1. And so we can write this now as 2m plus, well, this right here is the only one that is 2n plus 1, not this 1 right here, because we will have that as 1 minus 2n plus 1 over our m plus 2 times m plus 1 multiplied by our a sub m. And so this right here will simplify down, and we can say that that is equal to 2m minus n over m plus 2 times m plus 1 times our a sub m. So this tells us that this terminates, so it terminates, and when I say terminates, I mean it stops being a power series and becomes a polynomial when m is equal to n. And we can see why that would be the case, because if m is equal to n, then this becomes 0, and the next a m plus 2 will be 0, and that's where the power series terminates. And so if we use this relation, this recurrence relation here, to calculate using the different n's, so if we have our function here, and we say that that it's for a particular n, and it's a function of our xi, which just a reminder, our xi is proportional to our x, and our x is measuring the position uh, away from the origin. So we have our origin here. So x increases this way, and well, the magnitude of x increases this way, and so our xi is proportional to the distance from the origin, the distance from the lowest point of our potential here. And so we have our nth f here. So f where n, if we have n equals 0, then what we have is f with 0 there of xi is equal to a sub naught times xi to the 0th, and we know that that anything above that is going to terminate because our m is equal to 0 here, and so is our n, and so this is the highest term here. And so this will just end, xi to the 0th is just 1, so we end up with a sub naught. And if we have n equals 1, what we end up with, so f1 of xi is going to be equal to a sub 1. And so I guess I should have pointed out too that we're saying that when n is even, that all odd ends are going to be equal to that all odd, I guess I should say all odd a sub n's, or I guess if we wanted to make it clearer that that's odd, 2n plus 1 will equal 0, that if n equals odd, that all even, and so we can say that that is n, 2n will be equal to 0. So we are not having an a sub naught term in here, and so that is a sub 1 times xi to the 1th power, and so that will just equal, and we end up writing it in this sort of weird way because that helps us make it look like the Hermite polynomials, and so we will have it a sub 1 over 2 times 2 xi, and that's to the 1th power, so it's just xi. And we can see that these 2's cancel out, but if we put it in this form, then we can compare it to our Hermite polynomials. And if we have n equals 2, what we end up with is our 2 xi, and that will equal a sub 0 over 2 times 4 xi squared minus 2. And we could keep going, so if we have n equals 3, I'll make this the last one that we'll look at here. N equals 3, so f3 of xi is going to equal a sub 1 over 12 times 8 xi to the 3rd minus 12 xi. And we can compare these to the Hermite polynomials. So if we look at Wikipedia, so our first one here is our a sub naught, and we could sort of put a 1 in here. So this 1 here would be our actual Hermite polynomial, and we have 2 xi here, and so we can look at this, and we have 1 and then 2x as our first two Hermite polynomials. Then we have 4 xi squared minus 2, which 4x squared minus 2 is our second Hermite polynomial. And we have 8 Xi cubed minus 12 Xi, which is just like our 8x cubed minus 12x. And so if we kept calculating, we'd keep getting these polynomials right here. And that's why we have this weird way of putting this out here, this a sub 1 over 2, is so that these in parentheses all look like our Hermite polynomials. And so these are the Hermite polynomials here, which, as I said in the previous videos, that we were going to get a wave function as a function of position, and I guess I could write the position as Xi here was going to be equal to a sub n times our Hermite polynomials times our exponential function, which was the exponential of minus Xi squared over 2. And so that is, so we have now gotten to this point here. So we got this from looking at the behavior of our differential equation as Xi went to very large numbers, as it went to infinity. And now we have just gotten this h sub n, which are our Hermite polynomials. And so now we can say that a sub 0 and our a sub 1, we can say that those are like our a sub n's. And this is for a normalization. This is a normalization factor. And I will show here how we actually get that. And so we know that to normalize it, that we need to have it so that, so in general, the integral from negative infinity to infinity of our wave function, the complex conjugate of our wave function times our wave function has to be equal to 1. And so if we convert this into what we have been using, so we've been using Xi instead of x, and so that gives us this h bar over m omega square root times our integral from minus infinity to positive infinity of the complex conjugate of our wave function as a function of Xi times our wave function as a function of Xi, and I guess I should put a dx over here as well. So dx, because this will have d Xi, and that will have to equal 1. And so if we know from up here what our wave function as a function of Xi is, so we can just substitute that in for these psi's here, and what we end up with is h bar over m omega square root times the integral from minus infinity to infinity. And so then we have our first wave function here, which is the complex conjugate of a sub n, the nth Hermite polynomial, which is a function of Xi, times our exponent of minus Xi squared over 2. And so that is complex conjugate times a n h n of Xi times exponent of minus Xi squared over 2 d Xi equals 1. And so from this we can just sort of multiply all the like things through, and what we end up with, so this an is a constant, so we can take that outside the integral, so we still have h bar over mass times the angular frequency, and then we have a sub n squared times the integral from minus infinity to infinity of h sub n, the nth Hermite polynomial squared, times the e to the minus Xi squared. Because we multiply those through, that 1/2 goes away, and then we have d Xi equals 1. And so this is the integral we have, and then we have an integral identity, which is just the integral identity for the Hermite polynomial. So if you watched my videos on the Hermite polynomials in the differential equations playlist, what we have is hn of Xi squared, and so we know that this n has to be equal because we're just squaring it. We're saying that we have hm times hn, and I'm not going to bother writing those Xi's in, is equal to something times the Kronecker delta of mn. And so when we square it, we're just saying that this m and n are equal to each other, and so that's what this is here. Then we have our e to the minus Xi squared, and this is our weight function. So I talked about weight functions in my video on the Hermite polynomials, and so this, if the m and n are equal to each other, then what we get is 2 to the n times n factorial times the square root of pi. And so we can just put that in for our h sub n here, and then what we get is my cursor. All right, what we get is equal to h bar over mass times angular frequency square root a sub n squared, and so we just took this integral here and said that it was this right here. So then what we have is our 2 to the n times n factorial times the square root of pi equals 1. And so from here we can just do some algebraic manipulations. So we end up with a sub n squared being equal to, so we just divide both sides by this right here, and what we end up with, so that flips over and becomes mass times angular frequency, still square root, but then now we are also putting this to the other side, so we have 1 over 2 to the n factorial times the square root of pi. So we end up with this. Then we just do the square root of everything, and so we end up with a sub n. So a sub n being equal to, so now we have m times omega over h bar. So we took the square root of this, so what we end up with is the 4th root of that, then times 1 over 2 to the n factorial square root of pi. But now we have the square root of all of this, and so this square root of the square root of pi can end up going under this this fourth root here, and so what we end up with is m times omega over pi h bar to the fourth root times 1 over 2 to the n factorial, and that is the square root of that. And so now that we have this right here, so this all is this was our a sub n. And so now we can plug this into our wave function. And so what we end up with is the nth wave function is equal to m omega over pi h bar, and that is the fourth root times 1 over 2 to the n factorial square root times hn of xi times the e to the x of minus xi squared over 2. And so this is our wave function here. And like I said, it's in that form of a n h n, which is a function of something e to the minus something squared over 2. I said it was going to be in this form, and that is exactly what we have here. So this is our a sub n right here. And if you remember from quite a few videos ago, this is all using the time-independent Schrodinger equation, which we got from taking the Schrodinger equation as a function of space and time and doing a separation of variables. So we ended up with some function of space and some function of time. And so if we wanted to put that back together, what we would end up with is the nth wave function is a function of space and time. So now there's going to be a few more things in here because I've converted it back to x rather than xi. And so what we get is mass times the angular frequency over pi h bar, and that is the fourth root times 1 over 2 to the n factorial square root times the nth Hermite polynomial. And now because we are converting from xi to x, we will end up with a mass times angular frequency over h bar square root times x. So this is our xi here, and then times e to the power of minus m omega over 2 h bar times 2h bar x squared. So this is our xi squared, our minus xi squared over 2. And so we have that, and then we have that the time exponent here, which is minus I times n plus 1/2 omega t. So we've added this time element back into it. So we took the product of our spatial time-independent Schrodinger equation here, and then multiplied it by our time function here, just like what I showed up here. And so if we look at the plots of these wave functions, So on the left here is the wave function. These images are from the book I've been using, which is the A Student's Guide to the Schrodinger Equation by Daniel A. Fleisch. And so here we have our wave functions. So with our psi of 0 and 1 and 2 and so on. And this is what we would plot them as in our potential well here. So that's our V of Xi right here. And so if we then squared those or multiplied them by their complex conjugate, we would end up with our probability densities here. And so one thing to notice on here is that as we get to these higher energy levels, we see that we are getting these higher densities on the edges here. And we're getting sort of these higher frequencies in the middle. So I talked about that in a previous video, how because we have that Gaussian term, well, because we have it in the form, so if you remember, our differential equation was of the form, we had the second derivative, so I'm just going to use x here, because I'm sick of drawing she's, was equal to something like this, our epsilon plus our, I mean, it was she when we talked about it before, but I'm just using x to make things simpler. And so we said that this was the curvature here. This was the curvature of our wave function. We said that the curvature increases as the energy increases. So this was our energy term here. And you see that as we go to higher energies, we are getting this higher frequency here. But also, and this should be a minus right here, that as we get further away from the origin here, that the curvature should go down, and you can see that in the top here where we have the curvature sort of spreading out a little bit as we go to the top. And then we see after we get outside of the potential that this just exponentially decays. But the other thing I pointed out was that we have these higher probabilities at the edges when we are at these higher energy levels. And that makes sense if we go back to the analogy of the mass on a spring. And so if this is sort of moving back and forth, we know that at the edges it's going to be slower because the force pushing inward will keep getting stronger as we go to the edges. And so this slows down when it's at the edges of the well. So we have our potential well here. So as we get to the edge, it slows down. And so if you wanted to just plot where you are likely to find that mass, your probability of finding it at the edges is going to be higher because when you're in the middle, it's going really fast in one direction or the other. So it's not spending as much time there. And so we see that at higher energy levels, the approximation here of looking at it as a harmonic oscillator starts looking more and more true. And so that is why modeling this as a harmonic oscillator is a good way of modeling this. But anyway, that is, as I said, all I'm going to do for the one-dimensional Schrodinger equation with a potential model as a harmonic oscillator using the so-called analytic approach. So this is the, as I said, the so-called analytic approach. In the next video, I'm going to look at what is sometimes called the algebraic, or maybe the commutator commutator approach. And so I prefer the analytic approach. The algebraic approach is a bit more abstract, and to me it's harder to get an intuitive sense from it. So I'm not going to spend as much time on it. But I am going to go over it because it is a valid way of solving the Schrodinger equation, and it's a way that if you study this, you will likely encounter. And so it is worth going over, and that way we can also sort of make comparisons between the algebraic and analytic approach, and show how they are both valid ways of getting to solutions of the Schrodinger equation. But anyway, that will be the next video. The video after that, I am going to look at the Schrodinger equation for a free particle. And then after that, I'm going to look at the Schrodinger equation for a Dirac delta function. So delta function. And so what's interesting about that, so the delta function be the model of the potential. And so what's interesting about that, as we'll see, is that you have potential that's zero everywhere except for this sort of infinitely narrow, this infinitesimally narrow potential right here. And so if we have a particle, it will be free everywhere except here. And so what you end up seeing is that you end up with a term for the particle approaching, a term for the particle reflecting, and a term for the particle transmitting through it. And so that's probabilistic because there's a probability of it reflecting and a probability of it transmitting through the potential. But anyway, I'm getting ahead of ourselves here. This was the harmonic oscillator. I hope you found this useful, and I will see you in another video.